types of protein. Those we have, sorry.
Bien. Se desconectó ella, la desconectamos.
No, ahí está en pausa para que
Y dijo, tengo que buscar algo.
y ya no les dejan ahí quiénes son los que querían permitir entrar.
Y se puede,
¿Cómo podemos permitir que?
Sí. Buenos días, ¿se desconectó la doctora?
Sí, sí se desconectó, hay que esperar que se vuelva a conectar. A ver si pasó.
Ok,
Cuando...
ya está transmitiendo.
Ok. Hacemos. Ok. Cuando esté conectada, a ver si se pueden dar las cosas.
Yo lo que quiero saber es que le están pidiendo entrar. ¿Cómo vamos a hacer para diagnosticar la presentación? ¿Ingresan solos?
Está en la sala.
Porque no sé si ya está.
Ahí está.
Ya.
We come back.
Okay, I don't know what happened actually, sorry.
Oh, don't worry, don't worry.
Okay, so let's continue. Where I was. So maybe I'll just keep it small. Okay. So yeah, so I was explaining about the low moisture meat analog, and then we have this high moisture meat analog, and we have different protein and carbohydrate sources that we can use in order to produce this two different types of meat analogs. So we have different approaches that we can apply in order to have this kind of structure. Previously, we used to use electrospanning method, and which require a very high pure protein. That means we have to have 90% protein content in the sample in order to produce this kind of meat analog, which is highly expensive and difficult to do because the pure protein is very, very expensive. But now we have this extrusion technology that we are using it, so we do not need that much pure protein in order to produce this kind of TVP or meat analog. We can have 60 to 70% protein in the sample or less than that, and we can still get this kind of fibrillar structure, which basically the distinct characteristics of any animal-based protein. Now we have this plant protein, which is globular structure. That means the strand of proteins are intertwined and forming a ball-like shape. So how we can tune this kind of ball-like shape into a laminar shape? The laminar shape looks like somewhat like this. So we are using this extrusion technology. We can have two screw or single screw technology. So basically what we are doing, we will put our dry sample. It's important to use the dry sample in the feed hopper, and then we are going to mix it in this zone. So we have this feeding zone, compression zone, where basically melting the protein so that the protein structure become unfolded, and then we will use this metering zone where we will use this laminar shear flow so that we can have this laminar structure at the end. And here we have a dye zone, we call it forming zone. It's a cooling zone. Basically, after having that laminar structure, we want to cool it immediately in order to protect the structure in this laminar form. So this is the gist of the technology that we use nowadays. Okay, so these are some picture of the extruder. We have texturized vegetable protein. That's the low moisture content meat analog or meat substitute. You will see that small ball-like shaped. They are not. They will not look like this kind of high moisture meat analog because the moisture content is very, very low. The purpose of TVP is for the consumers who want an easy life, who do not want to refrigerate their sample. And also because it's a low moisture content, it's very much easy to store it for a long period of time. And by long period of time, I'm talking about 1 year or 2 years because the moisture content is super low. And for this product, it will not last for that long period of time. And plus, we have to refrigerate the sample. It's because we have 60% moisture content. So you will see this is the dye zone, cooling dye zone from, and at the end of the dye zone, we have this split. So product will come out. And then we have a cutter. We can cut the sample into the desired length that we want. And after that, we can season it and cook it. Okay, so these are two important criteria of the extruder. We have single screw extruder and we have this twin screw extruder. Nowadays, we use twin screw extruder with 4 rotating screw. This is much more gentle on protein structure. Counter rotating would be used in polymer industry, but for biological based polymer, we use a co-rotating screw. We do not want to be too much harsh on our protein sample. Okay, so I have a case study that I used for my research. We used a mung bean protein. So in the market, we have lots of soybean. However, some consumers have allergic issue to the soybean. Plus, this soybean have very strong taste, or flavor, which some of the consumers do not like. So we want to switch from soybean to any other alternative proteins that can be cultivated in a particular region. So in Asia, and especially in Malaysia, we have a lot of these mung beans. They have good protein content, and the good thing is the fat content is very, very low, 1 to 2%. So we do not need to extract the fat, and we can save and cut down some of the production cost. And apart from this basic nutritional factor, we have some extra benefit, that is the detoxification activities, and then reduction of cardiovascular disease and many more things. So basically, they are more than fulfilling our daily nutritional requirements. So we have 3 different goals. At first, because we are using a powder sample, and in order to create a powder sample, of course, we have to use this drying technique after we extract the protein. And there is a possibility that the characteristics of the protein sample might change. So we want to study that, what characteristics can be changed, and whether it is after the application of drying technique, whether it is still suitable for the production of meat analog or not. And second, we want to see the effect of that extrusion parameters on the texturized vegetable protein. And third, how we can basically detect the changes that has been made through extrusion technology. So in the beginning, we used these drying methods in order to make protein powder, and we have hypothesized that drying might have some effect on the protein because protein is very sensitive biopolymer. So we used a lot of pilot scale and a lot of mung bean flour, around 10 kg, and we used alkaline solubility because the solubility of protein in alkaline condition is very high. So we used sodium hydroxide in order to solubilize the protein in the water, and after that we used some hydrochloric acid in order to collect that protein that is solubilized in the water. And through centrifugation, basically, we can collect that protein. So this is our mung bean protein isolate. And do not worry, seeing this acid and base in the food sample, we have washed it thoroughly and neutralized the sample. And we have removed all the sodium hydroxide and hydrochloric acid from our sample. And after that, it appears as a dough-like consistency, and the moisture content is around 20 to 30%, which has to be reduced to 4 to 5% in order to make it into a powdery and glassy form. So we used 3 different kinds of drying: oven, freeze, and spray drying, and we wanted to see what's the effect of 3 different kinds of drying on its different functional properties. So we have these physicochemical properties, the functional properties. The functional properties is very important for the development of any kind of food product. Basically, this will tell what kind of food we can produce from analyzing this all the property. And then we want to see the molecular properties and some other thermal properties. Basically, in the extrusion, we are using high temperature. So we wanted to see the suitability of the sample or when it has undergone some high temperature. So first thing first, because it's a protein alternative, we need to see how much protein we got after extraction. So we got around 86% protein in freeze-dry sample, while we lose some of the protein when we apply heat. The SD means spray drying and OD means oven drying. So these two have some harsh effect on the protein, and we lose some of the protein in this too after this using this two kind of drying. And then not to forget about the amino acid. Amino acid is the building block of the protein, right? So it's very important. When we digest protein, the enzymes basically will break down the protein into all of these amino acids in our body. These are essential amino acids. So it's very important to see that we have this balanced amount of amino acid profile in the food. And we found that freeze drying have this gentle effect on this amino acid profile, and it retained most of the amino acid in our sample compared to spray and oven drying sample. Then some color properties. We have some whitish appearance for the spray drying sample, while some mild brown color for freeze dry. And for oven dry, it's a very, very dark color because the drying condition was quite long. And there is a possibility of some brown color pigment formation through Maillard reaction. That's why we got very, very dark color pigment formation, and which is not suitable for meat analog or any other kind of analog because it doesn't look appealing at the end. Particle size distribution. So we wanted to see how small the particle is. The spray dry is very, very small. So we discard the sample, just saying this mean diameter size, which is only 17. There is a high possibility that when we want to add water in the food in our recipe, this will agglomerate and it will cause problems. The sample may stuck inside the extruder and the texturization may not be completed. However, for the freeze and oven dry sample, we have this good amount of mean diameter and it's acceptable for the production of meat analog. From the scanning electron microscope, we can see that this freeze drying sample, interestingly, got its porous structure, which is very good because when we are adding water, it can absorb more and more water compared to oven dried sample, which is basically compact and more crystalline, and the spray dry is very much wrinkled structure. Okay, so protein solubility, it's just generally means that how much protein can be solubilized in water. The solubility of protein is highly dependent on its pH. Usually, for bean-based protein, they are highly solubilized in acidic and alkaline condition, and in neutral condition, they do not tend to solubilize much. Now, it's a key indicator in order to know how much protein has undergone changes. So at the beginning for our raw sample, we use this protein solubility, and we are going to do it after we produced our sample in order to see how much structural changes has occurred. So if there is a changes in the solubility, that means there is a changes in the structural organization of the protein. These are some functional properties, which is important for the food product development. Very simple analysis, but useful analysis. So we are seeing the water and oil absorption capacity because based on our recipe, we are going to use water as a plasticizer and some oil in order to have that emulsion or elastic biting appearance. So you will notice that freeze drying, because of its porous structure, it can absorb more water and oil compared to spray drying sample. Surprisingly, oven dry sample also have a very good water absorption capacity. However, it took a bit long time for oven dry sample to absorb the water. And for emulsion activity and stability, the spray drying sample have better characteristics. Emulsion, I must say the protein have the act as an emulsifier. That means it can basically join water and oil molecule together and form the emulsion. And the stability, emulsion will not be stabilized for a long period of time. When its equilibrium is set, it is going to separate it out. So it's also important to know for how long we can stabilize the emulsion. So for spreading sample, it's 351 minutes, which is quite good compared to freeze dry and oven dry sample. And for gelatin concentration means how much minimum amount of protein we require to form a gel. We want to go for a very, very low protein percentage, because if we go for 18%, that means we are requiring much more raw material, and that might cost a lot for the industry people. Okay, and for the thermal properties, as I mentioned, that because during the production of meat analog, it will go under high temperature. So you have to make sure that the protein content have good standing ability with high temperature. And we can see from TD, which is the denaturation temperature, is quite similar and high for all the sample. And denaturation enthalpy is also high for all the samples. So we can conclude that all of these samples basically are good to undergo high temperature ensuring process. Okay, so next we have, this is a very chemical analysis. We call it SDS page electrophoresis. So we want to see the molecular weight of the protein. If the molecular weight is changes among the sample, that means the drying caused some severe structural organization or backbone of the protein, which we do not want. And you will notice that all the bands are identical, and we found it at the same molecular weight. The M means it's a marker of which molecular weight is known. And by comparing this marker with 3 other samples, we can know the molecular weight of these 3 samples. And it's appearing at the same molecular weight. So we can say that the freeze drying, spray and oven drying, they do not have any harsh effect on the backbone structure of the protein. Okay, now we have this FDR spectroscopy, which is very quick analysis, and through this spectroscopic analysis, we can basically compute the secondary structural composition of protein. Now, protein have 4 different kinds of folding pattern in its own body. So we have primary folding, secondary folding, tertiary folding, and quaternary folding. So we want to see if there is any changes in the secondary folding. And through FDR spectroscopy, we can calculate that very easily. So in secondary structural composition, we have beta sheet, random coil, alpha helix, and beta turn. So if we have more beta sheet, that means or more beta turn, that means they have undergone some structural changes, they have unfolded, and later on they have refolded again, because these are complex structural organization. And random coil and alpha helix, if we have more of it, that means it's much more native protein, that means unprocessed protein, and much more better compared to beta sheet and beta turn structures. So again, it's proving that this freeze drying sample might be a better candidate for our meat analog structure. And this is a dynamic rheological study. That's the temperature sweep. What we do is that we add some temperature, and along the temperature, we will wait for 90 minutes to see whether it can form an elastic gel or not, which is very, very important because meat have that gel structure in it. When you bite it, you will feel that sensation that's coming from gel-based characteristics. So if our sample cannot form a proper gel, most likely it will not be suitable to produce a meat, animal-based meat protein. So for freeze drying sample, we have this G prime that is increasing with time, telling us that it can form gel, and also the gel characteristics is elastic. And also our oven dry sample can form gel, however, because the G double prime, which means the viscosity is much more higher compared to the elasticity properties. So it will form much more aggregated gel rather than forming elastic gel. So we are not interested in forming something viscous or aggregated gel because they will easily crumble when we bite it instead of giving that elastic chewiness sensation. However, our spray drying sample could not form any kind of gel. So from this chapter, we have concluded that because of all the positive analysis, we can say that freeze drying could be a better candidate for producing animal-based meat protein. For spray drying, because its emulsion properties is good, we can form some meatloaf or sausages, not something like extrusion technology. Some basic properties, basic food product development. And for oven dried sample, we can produce general protein-based food. Now they have good water and oil absorption capacity. We can go for some beverages, protein-based beverages, or some weak gel-based product. For example, viscous sample, for example, tomato soup or ketchup, something like that. So this will act as an additive, not if you want to make your tomato soup or ketchup much more viscous, then you can use it as an additive, but not as a sole ingredient, just to clarify that. Okay, next we have the effects of extrusion parameters on the texturized mung bean protein isolate. So in this chapter, we want to produce our TVP. So one of the another reason that using extrusion technology is that most of the legume, they have these anti-nutritional properties. They have some components in them that may reduce the protein absorption in your body. That's why traditionally when we cook legume, basically we will soak it for a long period of time, 24 hours, or we will cook it under high pressure. So those can eliminate some of the anti-nutritional factors, but it's a long standing time. Nowadays, we are much more busy and we want something very quick. So this extrusion technology is an quick alternative to reduce this kind of hard to cook phenomenon and to reduce this kind of anti-nutritional factors. So we used around 30 recipes in order to produce our sample. We use the CCD design, central composite design. We have our independent variables, that is barrel temperature, screw speed, and feed moisture that's coming from our extruder. We have some minimum values and maximum values, and we have some dependent variables. That's the expansion ratio, bulk density, rehydration ratio, water absorption index, and degree of texturization. Now, before doing these 30 recipes, we have conducted around 20 more recipes to know what would be the minimum and maximum value and to know what we are looking for in terms of expansion ratio, what's our desired value. So that's how we develop a food product. First, we have to know these properties, what's our desired value, and then we use some random independent variables. After that, we can know that what possibly could be the minimum and maximum value. Okay, so after we have done our laboratory small study, then we again conducted another study that containing 30 more recipes using these 3 independent variables. Okay, so this is some RSM plots, response surface plot. From the different shape of the figure, we can tell that these different independent variables have good amount of effect on these 5 different dependent variable. I'm not going into very much detail because that wouldn't be very much related for today's session, but just as a gist, I want to say that after having these 30 recipes analyzed, we have found our optimized processing condition. That's the important thing. We cannot just randomly choose any kind of variables. We have to optimize the condition based on our predicted value that we have found before conducting this 30 recipes. So we already know what we're looking for. Now we want to see if this optimized condition can produce this predicted value. So after we have this optimized condition, which is written in red color, 49% moisture, 80 RPM screw speed, and 140 degrees Celsius, we have conducted another 3 experiment using this optimum condition when we have found this experimental value, which is similar to our predicted value. So we can say now that this is the extrusion processing parameters that we want to use for the development of texturized vegetable protein. And our industrial partner, they can even use this optimized condition to produce meat analog from mung bean. It may not be suitable for other protein because each of the plant protein have their unique properties. So this is a case study, it's only for mung bean protein. And next, what we did is scanning electron microscopic analysis, which is very useful tool in order to know the surface morphology of the structure. So before because it's a low moisture food, before hydrating our sample, we found that we have some porous structure, some small fibril structure formation. And when we hydrate it, the pores are gone because it's filled up by the water, and the fibril structure is joined. Now it will give you a gel-based food structure sensation. So, which is good for our, which fulfilled the ultimate goal of our study. And again, we have checked the amino acid because ultimately it's not about structure, it's not about taste, it's about this amino acid, which has to be absorbed in our blood. Otherwise, we're not getting any nutritional benefit out of it. So we found that the extrusion condition have very gentle effect on our sample, and we were able to retain around 92% of essential amino acids. Yeah, and specifically, I have mentioned lysine here. The retention ratio is 89%. If you cook through traditional methods, you are going to lose this lysine more because this is very heat-sensitive amino acids. We lose it a lot when you use traditional cooking. However, because it's a quick process, the extrusion requires around 5 minutes to do all the processing, and you will see your product is coming out at the end after 5 minutes. So it's a very quick method. Even though we are using a shear stress, high temperature, but because it's quick, so it has this gentle effect on our acid profile. So this is again, we have done the SGS page electrophoresis. This is our raw material. You will see this native mung bean protein isolate without going any kind of processing. We have these 5 bands in here. However, after extrusion, you will see we have only 1 band at this 37 kilodalton. And interestingly, when you use high moisture, that is 60%, and very low moisture, that is 30% at different temperature, nevertheless, we reduced 4 of the bands, that because of the changes in the structural organization of the protein. But when you use our optimum condition or around intermediate moisture content, which is 45% or 49%, we were able to preserve a structure which is similar to this native protein. That's what we're looking for. We do not want to completely change our protein structure, because when we completely loosen up the structure, it will basically lose its functional properties, which is very important for food. So we want something that is partially unfolded, not fully. And that's why we have conducted this analysis in order to know whether it's a fully unfolded protein or partially unfolded protein. We found again that our optimized condition is much more gentler, and we can use it and comparable when it's with the native or unprocessed mung bean protein isolate. So native protein is better, it's always better, but for the food product development, we cannot go for an unprocessed protein sample, right? At the end, we have to make it our desired food product, so we must go under the processing condition. However, we want something that is a gentle on the structure, a gentle processing condition. Okay. So next we have this the extrusion-induced changes on the structural and rheological properties of texturized mung bean protein. Now that this chapter actually led us to do this the next chapter, because we found these changes happening, and we want to have more confirmation that why it's happening and how we can explain it. So we have done some structural properties, for example, using FTIR, circular dichroism, fluorescence spectroscopy, and some other properties like thermal and rheological properties. This is more for the functional properties of the food. Okay, so as I mentioned earlier, protein solubilities, it's an indicator to know whether our protein is completely folded or partially completely unfolded or partially unfolded. So you'll notice basically the protein solubility is increased, which is good for us. That means our sample is able to absorb more water. It can interact with the water more readily, which is good. So we have the 75% solubility, which is comparable to our native protein, 71. But when you use very low moisture, 30 and 60%, the solubility is reduced a lot. So these two samples are not good for the food product development. Next, we have thermal properties. You will notice that protein denaturation, and then this enthalpy reduced by twofold than before. This is 158 and 19 because the structure in the native is much more compact. However, when we use shear technology, shearing stress, and then high temperature in the extrusion barrel, we have loosened up the structure, and that's why the denaturation temperature has gone down, plus the denaturation enthalpy as well, because the structure is unfolded now. Okay. Next, we have circular dichroism. So this is also to compute the secondary structural composition of the protein. So of course, all the sample, the relative ellipticity is reduced because of the structural changes compared to the mung bean protein isolate. Yep.
Yeah, yes.
And then next we have this FTR analysis again for the secondary structural composition, and we have noticed that for 30 and 60% we have more beta turn structure, which again telling us the complex structural reorganization in this low and high moisture food compared to our optimized condition, which is 49% moisture content. Yeah.
Thank you so
And then we have this intrinsic tryptophan fluorescence, which basically we use our sample to understand the third folding. That is, we call tertiary folding of the protein. As I mentioned, protein have 4 folding. So this is the third folding that we have. And even at the third folding, we have some changes in all the sample. The 393 lambda max is for mung bean protein isolate, which is unprocessed. For the red color, which is 30%, and purple, 60%, they have gone down a lot, and then the intensity also very much less, which is showing us again that the third folding has also been changed after the extrusion.
Thank you so much.
And then next we have this frequency sweep. So we just want to see if the protein can form gel after the extrusion, because we have unfolded the structure so much, and we found that the 49% was successfully able to form the elastic gel. You can see from G prime, it's a straight line that's showing the formation of elastic gel. However, other sample could not produce this elastic gel because the G prime is going down along with the frequency, with the increase in frequency. So just to conclude that we basically proved that the Y 49.3% moisture content showed the desirable qualities, yeah, compared to 30 and 60% protein. And all the secondary structural properties of protein can be successfully analyzed using circular dichroism and FTIR and other spectroscopic tools. So now we have a collaboration with Professor Felipe to see how we can basically analyze the structural characterization of any other plant-based meat analog using microscopic and spectroscopic analysis. So that's all for today. Thank you.
Fatima, can you hear us?
Yeah.
Okay. Thank you very much for your conference.
Okay. Thank you for inviting me.
Thank you. And we don't have time for questions, but if people has questions, we will send you by mail, or we stay in contact with you.
Okay, sure.
Thank you so much for your time.
Okay. Thank you. Thank you so much.
Póngale, por favor, si ya no se escucha.
Profesor Usala, dice aquí, no sé si la cámara.
Pues yo, no sé en dónde me oyó.
Yo sé si de acá. Yo digo que de la compu, por el micrófono de la compu. Y ahí está el micrófono.
Usala, good morning. Can you hear us?
Good day, doctor.
Good morning, Professor. We
Good day.
are here. Thank you very much for your assistance. Can you share your screen, please, to present you?
Okay.
Eso lo está tardando sonido.
And I was by thinking and at first specifically by the doctor who's maybe have as a variant stable and using university in a survey. I don't know from the doctor who's maybe from
Usala, Dr. Usala,
Yes.
you can begin now your presentation.
Okay.
Thank you.
Okay. Hello, everybody. Can you see? Hello, everybody. My name is Usala Jafarova. I am associate professor, Department of Physics of Azerbaijan State Oil and Industry University. I want to talk about the first principle simulations of cobalt and nickel dope, simulation of electronic and magnetic properties of transition metal doped zinc selenide. Diluted magnetic semiconductor materials enable the development of spintronic devices with potential to operate at considerably higher speeds while consuming less power than conventional devices. These materials have allowed the production of new types of materials with the most important technological applications in spintronics. Spintronics is one of the most promising next-generation information technologies which uses the spins of electrons as information carriers and possesses potential advantage of speeding up data processing, high circuit integration density, and low energy consumption. However, spintronics faces a number of challenges, including spin generation and injection, long distance spin transport, and manipulation and detection of spin orientation. In solving these issues, new concepts and spintronics materials were proposed one after another, such as half metal spin gapless semiconductors and bipolar magnetic semiconductors. In designing these spintronics materials, first principles calculations play a very important role. Zinc selenide could be used in spintronic devices only if additional dopants are introduced. Zinc selenide is a diluted magnetic semiconductor material which exhibit both ferromagnetism and semiconducting properties. This material semiconductor can manage as a half metallic property and is an advantageous material for spin-based device applications. The magnetic semiconductors are used to make quantum computing architecture using spin polarized electron and in magneto-optic applications. Due to its potential applications in several optical and electronic devices and as a buffer window material for thin film heterojunction solar cells, it is seen as an important technological material. The pure zinc selenide layered semiconductor has non-magnetic properties. The investigated compound is a direct wide bandgap material. It has great potential for optical devices such as blue-green laser diodes, short wavelength lasers, pure green light emitting diodes, from microwave to terahertz devices, solar cells, to enable mid-infrared laser origins. These 3D transition metal doped systems have great research interest by science as efficient applicants for a new generation for spin-based devices. This research work is devoted to analyzing of the electronic and magnetic properties of transition of 3D transition metal doped zinc systems with concentrations of 12.5 and 6.25 impurity concentrations. And for this we implementing the local spin density approximation and Hubbard-U methods based on density functional theory. Key sampling host pack Greece 555 used and all atomic positions have been geometry optimized. The valence electron configuration which included 12 electrons for zinc, 6 electrons for selenium, 10 electrons for nickel, and 9 electrons for cobalt were taken into consideration. The kinetic cutoff energy of 50 Hartree was employed throughout the calculation, which was tested to be fully converged with 4 to total energy. How about you to obtain the more correct band gap structure? We use Hubbard-U semi-empirical corrections for U parameter 4.5 electron volt for these states of zinc and 3.8 electron volt on p states for selenium atom. Selenium atom and all calculations carry out using the atomistic toolkit program package. In this slide, you can see the transition consists of is first principles calculation results of 32 atom spatial structure. Spatial structure. This is a spin up band structure, and this is a spin down band structure. And this figure illustrates the total density of states for no, sorry, this is the band structure and the total density of states diagrams for undoped zinc selenide. We see that this compound is a direct band gap semiconductor material. The wide of band gap is equal to 2.7 electron volt. Note that these calculations were carried out using the local densities, local spin density approximation, and implementing the Hubbard corrections. And in this slide, you can see the cobalt zinc selenide systems for both spin up and spin down structures. We see that the cobalt zinc selenide spatial structure shows a semiconducting nature. And here in the spin down band structure, we see some of the impurity levels can be found near the Fermi level, Fermi energy level, which mainly form from 3D states of the cobalt and 4p states of the selenium. Cobalt doped zinc selenide has no half metallic character. And in this table shows the results of band structure, band gap results for the 12.5 and 6.25% concentrations. In this slide, you can see the results of our calculations for nickel doped zinc selenide spatial structure. Consists of 32 atoms. The figures illustrate that the spin-up band states for this structure has a semi-metallic nature due to the top of valence band cutting the Fermi level, and we can say that nickel doped zinc selenide has a half metallic behavior for all studied concentrations of impurity atoms. And in this table, you can see the results of band gap values for nickel doped zinc selenide spatial structure. Here you can see the total density of states diagrams for cobalt doped and nickel doped zinc selenide spatial structure. The obtained density of states showed between the selenium P and cobalt nickel D states showed the hybridization of selenium P states and impurity D states. To understand the origin of the spin polarization notation of the density of states, we analyze the partial density of states for host and impurity atoms. These partial density of states for both systems presented a similar behavior. They illustrate the valence band formed mainly selenium P and the impurity D states of impurity atoms. The fig and then we investigate the magnetic properties of doping systems. In this slide, you can see the results of magnetic moments for cobalt doped zinc selenide and the total magnetic moment for this system to be equal to 3 magneton bore. The integer number of magnetic moments per supercell is mainly due to impurity atoms. Mainly contribution from these states of impurity atom cobalt. In this figure, you can see the spin polarization view for cobalt doped zinc selenide system, supercell system, and the black arrows show the magnetic moments. The computed value of magnetic moments per impurity is found to be 2.3 magneton bore. Main contribution from cobalt D states, approximately 2 magneton bore for cobalt doped zinc selenide system, and the insignificant negative contribution to the magnetization from zinc host atoms and positive contribution from host selenium atoms. The significant positive contribution from 4 selenium atoms with chemically bonded cobalt impurity atom. Then we have been calculated the total energies for ferromagnetic and antiferromagnetic states for investigated systems, and the results of the total energies show that cobalt doped zinc selenide system is a stem for this the antiferromagnetic states more stability than ferromagnetic states. In the case of nickel doping zinc selenide supercells, that the total magnetic moment of for this system equal to 4 magneton bore, and for the nickel atoms, the local magnetic moment about of 1.2 magneton bore. The main contribution to the magnetization from these states of nickel atoms, the small negative contribution from zinc host atoms of special structure. The significant positive contribution from 4 selenium atoms with chemical bonded with nickel atom. In this figure, you can see the spin polarization view for nickel doped zinc selenide structure, and the black arrows illustrates the magnetic moments. In this table, you can see the results of total energy calculations for antiferromagnetic and ferromagnetic phase, and the results show that the ferromagnetic stays more stability for than antiferromagnetic stays for nickel doped zinc selenide supercell structure.
We have 2 minutes.
And we also calculated the formation energy and the Curie temperature for investigated systems using these formulas, and the results for these parameters you can see in these tables. In this table, you can see that cobalt doped zinc selenide systems, for these systems, the Curie temperature negative, and this system
We have 2 minutes more.
these systems are suitable for electronic devices, and cobalt doped zinc selenide this system has no half metallic behavior, and nickel doped zinc selenide, these doping systems show high temperatures than room temperature, and this deleted semiconductor material is a promising candidate for spintronic materials, and nickel doping zinc selenide show half metallic ferromagnetic properties. These are conclusions of our research. Using an accurate density functional DFT LSD plus U approach have been explored the spin polarized electronic properties of cobalt and nickel doped zinc selenide systems with impurity concentrations 12.5 and 6.25%. While the introduction of impurity nickel or cobalt ions in the doped zinc selenide system change the total density of states, the obtained density of states shows hybridization between the selenium P and the 3D transition metal D states of metal D states, which increase the antibonding state in the gap and show stability of this FM state for nickel doped zinc selenide system, and antiferromagnetic state stability for cobalt doped zinc selenide. The obtained values of total magnetic moments have been found to be 3 and 4 magnetic bore for cobalt and nickel doping systems. And the main contribution to the magnetization comes from these states of impurity atoms. Nickel doped zinc selenide systems behave half metallic ferromagnetism and seem to be potential candidate for spintronic materials, but cobalt doped zinc selenide stems has a semiconductive nature, and the cobalt doped zinc selenide material is a promising material for electronic devices. In this slide, you can see my published list of published papers in this field. And thanks for your attention. Have you any question?
Doctora Busala, you hear us?
Yes, please.
Thank you very much for your conference. Questions? ¿Alguna pregunta?
Thank you very much, Doctor, for invitation. Thank you very much.
Thank you, Professor. Thank you very much. And
We appreciate the presence of the Dr. M. Visuala at the EMDA Congress, and we say goodbye to her with a lot of applauses. Thank you so much.
Thank you very much. Thank you.
We continue with the last conference in the first section called Effect of Cooling of Powder Generated by Photovoltaic Panels by Dr. Jonot Christian Scouter. Are you here, Doctor?
Yes, I can hear you. Can you hear me?
Yes.
I'll share my screen in a few moments.
So much.
Can you see this PowerPoint presentation?
Yes, we did.
Thank you very much. My name is Ionuț Cristian Scurtu. I am from Naval Academy Mircea cel Bătrân, Constanța, Romania, and I will present to your esteemed conference, the 4th International Conference Altamira on Materials and Devices. I will present the effect of cooling on power generated by photovoltaic panels.
Could you do a little bigger?
A little bigger. Okay. Can we see it just like that? It's okay?
Yes, it's okay. Thank you so much.
Thank you very much for telling me. Okay. In part of Naval Academy, Mircea cel Bătrân Naval Academy, which is founded 150 years ago. Today is a festive day. The 7th of November, 1872, is the start year of our school as the name of the fleet school. So today we have 151 years of naval learning in Romania, learning education in Romania. So this is part of our naval education in Romania. I will post here some of my competencies in order that you will know. If you want, I invite you all to contact me in order to develop partnerships. So this is my certificate of completion in ANSI software this year. I graduate this each year here in Romania, and the ANSI software is a workbench with a lot of competencies and a lot of parts. So I'll tell you what to look into. I am competent in electromechanical simulation in ANSYS, thermal and flow simulation, laminar and turbulent flow, aero and hydrodynamics, mechanical and thermal simulation. You will find also on the internet, on Clarified Profile, you will find all my publications with affiliations in Naval Academy and also Constanța Maritime University, because I have classes in both of them. You will find also online my Scopus profile with more than 46 documents. Maybe at this end of the year, I will bypass the 51 document, and I have more than 200 citations. So I'll start my presentation related to effect of cooling on power generated by photovoltaic panels. This paper is prepared with my colleagues from Technical University of Iași in Romania the Civil Engineering and Building Services, Romania. And I am the one presenting to you this paper today. And I'm from Naval Academy, as I said before. This part of the paper presents the operation of photovoltaic panels integrated in fixed position on roofs or facades of the buildings, because my colleagues are from Technical University of Iași, and they work with buildings. Knowing that the efficiency of photovoltaic panels is temperature dependent, and due to fixed position of photovoltaic panels, the panels are improving their conversion of the light into electrical energy by the temperature change. So we designed and discussed a few things related to cooling of these photovoltaic panels that are fixed on the roofs or the facades of the buildings. So the solution proposed for this paper for cooling consists in using water heat exchangers attached to the backside of the photovoltaic panel. It's a very difficult and tricky solution and old one, but is very has some good results. The results highlight the direct dependence of the photovoltaic efficiency with the temperature, and I'll present it to you in this in the next slides, for different positions in the same geographical location. The energy gain during the cooling interval is about 26.9 watts per square meter in vertical position, and 81.9 watts hour per square meter in an inclined position, and also 81.7 watt hour per square meter in a horizontal position, which represents 5.8, 9.3, and 9.2 respectively, compared to the normal operating condition difference. So the photovoltaic effect, this is only for the ones who have no idea of how a photovoltaic panel works, but a very small information here. In the right corner, we have the picture of the photons, which are determining the photovoltaic current. So the light, the photon with low energy, hits one electron, energizing the electron, which jumps on the superior orbital and participates in conduction. This is how it works, just in a very small part. So let's see in the figure below the dependence between power, voltage, and current in with operating of the cell. So we have here temperature from 0 to 75 degrees, and we have here some values normalized according to our variations. So we have the current with red. You can see that the current is increasing with the temperature, and we see the power decreasing and also the voltage decreasing with the temperature. So these are the relations between power, voltage, and current. And we have here intersection point at 25 degrees. We can modulate this current for a typical day of summer in July, Constanța, Romania, because I live in Constanța, Romania. And we took all the values from here, and we can analyze three main positions: vertical south, inclined south, and horizontal, where the intensity of solar radiation is considered to be variable during the day. So we use the simulation conducted in this software, TRNSys. This is how we call it here. The model presented in figure below show the blocks of climatic data for a polycrystalline photovoltaic panel. So we have weather data from Constanța, Romania. We have temperature conversion. We have the photovoltaic panel. We have a calculator to generate for the generated power. We have the output data, and we can convert this and we can calculate the efficiency using this software. So these are some results, and I'll put you some values. The maximum power point it's at a current of intensity of 7.88 amperes, and the net module area has a surface of 2.06 meters. So some of the data are presented here, and I'll post you in few moments on the chat to everyone. I'll post the presentation if you want to see these values, which are under normal operating conditions. So according to our, in the left, we have a variation in voltage intensity in this second column. I know that you love graphs, and we have here the intensity of the solar radiation with yellow. You see that we have a variation in Constanța. Probably in your country is the same. And this is the temperature outside. Look, the variation with blue. Temperature of the cell is the red line. And this is the power generated with green, which has a variation here in very vertical position. So let's see the results. This is the most important part. So we have here the power generated in normal conditions with blue. And we see here at 12 o'clock, for example, we have 73 watts per square meter. And we have with red the power generated in cooling conditions. For example, at 12 o'clock, we have 78.1 watts per square meter. And we put here the difference with green, additional power generated by cooling, which is 5 watts per square meter. So there is a difference with this cooling. We can calculate the performance improvement by calculating the electrical efficiency at the reference. So we can do that. We can provide and improve performance of the photovoltaic panels with cooling. So I put here some of the conclusions of the result and the results. And the results underline the direct dependence of photovoltaic efficiency with the operating temperature of the panel, which is already known. And the analysis and the data provided for each panel we used in our paper. For each system implemented, depending on its location, in this case, the location is Constanța, Romania, position, and we already told you that we used a vertical, an inclined, and a horizontal position. And also the time of the year is depending, it's dependent. Thank you for your attention. I encourage all your attendants to contact me in case they want to work together with me and to improve their publication skills or their simulations. And I want to thank you all for attention. Thank you very much.
Thank you so much. Now we are going to start with the question section. So one of you have a question, a comment, or someone to say?
Si tienen preguntas en español, se pueden traducir.
In Espanol, it is possible to understand, but I'm not sure.
¿La digo?
Sí,
Porque, ¿sí me escuchan?
sí, sí, sí.
¿Por qué la posición de la celda solar afecta o importa?
Why is important the position of the cells?
Understand your question. This study was made it is important because we have a different radiation solar and we have another efficiency in the panel. And also the temperature is very dependent on the position of the photovoltaic panel.
Thank you so much.
the efficiency is different. Yeah. Thank you very much for this question. This question shows me that you know very well how photovoltaic panels work. Another question. Thank you very much.
Yes, we have another. Wait a minute, please. Could you hear him?
No, I couldn't hear you.
Could
Can you please repeat?
I don't think so. How is the percent of the benefits?
What is the percent?
Yeah.
Of the benefit? As I said before in this presentation, you can see in our results here that we have, for example, an increase from 73 watts per square meter to 78 watts per square meter. So we have 5 watts per square meter increase in the cooling conditions. And we have to think that at 12 o'clock, we have temperature, the highest temperature here. That's why I said 12 o'clock here, which is, let's say, for temperature of the cell is more than 40 degrees. You can see all this data here. We will post the presentation in the chat with a link for transfer. Thank you very much. Hopefully this was good enough. My response was good enough.
No? We have another one, Professor.
Thank you very much. Thank you very much.
Dígala así. If you want, you can come here and ask by yourself. We have one more question. Wait a minute.
Okay.
Hello, can you hear me?
Yes, I can hear you.
I want to know what are the materials that you use in this photovoltaic and this device as well.
No, we didn't use a specific material. We have a fixed, solid, rigid photovoltaic panel, which is a commercial one, not a specific material. So we use the fixed, solid panel with a surface of 2.06 square meters.
Okay.
It's a commercial panel. I hope my presentation was good enough and I get your attention. And I'm very, very pleased that you have questions and I really enjoyed that. Thank you very much.
Thanks to you. It was really clear. Thank you.
Thank you so much for sharing with us part of your work. We send you a thank you and a big applause.
And thank you very much.
Thank you so much. We finish right now the first part of the conference. You can go to the break, the coffee break if you want. Thank you so much.
Thank you, guys.